Hello, I'm Greg, and today I want to talk about naturally occurring organohalides. So I was mainly inspired by this book, and was it around 75 years ago, we started detecting chlorinated and halogenated pollutants in the environment. And so this is naturally a concern because we really thought that, once they enter the environment, they're going to stay in the environment, and, it's going to be a whole lot of tedious work to remove them out because the time we did not know that bacteria have evolved to eating these things, It's like, at the time, we did not know that bacteria could eat these pollutants because we mainly thought that there was no naturally occurring organic halide stuff. So we thought, we can't use bacteria to, clean it up because bacteria took millions of years to just evolve, and now this stuff, never seen before in the environment, and bacteria need millions of years to start eating it. By that point, it's probably going to be all pollutants, constantly, everywhere, But as it turns out, there's actually some naturally occurring organic halides. And so bacteria really did exist before that can gain energy from doing dechlorination, debromination, or whatever. And so they very much exist, and they could very much eat our halogenated pollutants. I was mainly inspired by this book, and so I do recommend it. Again, source is here, and you can find the description, like slide 2. It's going to have a brief description of the source, and then the actual source. It's going to be a link. So this video is really meant to show you a new perspective on pollution, a much more hopeful one, I guess. And I want to talk about selected examples of organohalides, because there really are millions. Not millions. Well, maybe there are millions, but we don't know that much yet. I think the most recent number I saw was 20,000 known naturally occurring organohalides. But yeah, anyways, I just want to present you some very select examples of organohalides and what it means for biodegradation of PFAS. So what are halogens, right? Halogens are a very unique class of elements on the periodic table because they have very various properties. So organic chemistry is mostly the chemistry of carbon and hydrogen. And so when we look at compare the carbon radius to other halogens, right? The halogens, fluorine is smaller, chlorine is just about the same size, 80 to 70, right? And bromine and iodine are vastly larger, right? And so this is kind of important because one way to think about bonding is through symmetry. So let's say you have a number scale from -10 to 10. If you sum up all the numbers, it's going to be 0, right? It's going to be balanced. But what if you have 10 on the left and 7 on the right, right? And you put it on a scale, it's not going to be balanced, right? It's not going to be, balanced. But it would be much more favorable if it was perfectly balanced and summed up to 0. Basically. So these halogens have various degrees of symmetry. Some of them are nearly, iodine's almost double the size of chlorine, but fluorine is smaller than it, right? And so halogens offer this very unique property of bonding. Another key characteristic of halogens is their electronegativity, their ability to be greedy for electrons. So when you take chemistry in high school, I didn't take chemistry in high school, but I'm assuming they teach you that covalent bonding, VSEPR model, way to approach bonding, and that each element donates 1 electron, and they share it. That makes a bond. And then you hear probably about ionic bonding, which is where basically when there's such a great difference between the two elements in terms of their ability to steal electrons from each other, that one of them just permanently steals it from the other. However, as you get higher into chemistry, you really learn that it's more of a gradient between these two types of bonding. And like you could really describe ionic bonding and covalent bonding by the same model, and like something isn't like, even though something, and let's say between NaCl, right, the chlorine is much more electronegative than the sodium. There's a 99% chance you would find that electron on the chlorine, but a 1% chance you'll find it on sodium, right? And so it's much more accurate to describe bonding as a gradient, right? So like fluorine is nearly iconic in comparison to iodine carbon bonds, right? Like 2.7 versus 2.6, right? That's basically covalent. It's basically the same thing. It's basically evenly shared. And meanwhile, fluorine is at like a 4, just basically stealing it all for itself. And then you have bromine and chlorine that are basically doing the middleman, the average, right? And so, again, I'm just going to give you selected examples of halogen naturally occurring organohalides. First one being iodine. Basically, this iodine molecule is quite funky. As you can see, very, very, very funny structure. But this is actually very important to get oxygen to your brain, apparently, and it's actually very important for health in like children. I am not a biochemist. This review sums it up very well, and it's like pure biochemistry, and I was like, okay, you know what, I'll trust you. But like, here's the thing about iodo compounds, is that they don't typically last very long. The carbon-iodine bond is pretty weak. It's not very symmetrical, right? It's nearly double the size. On top of that, it's almost purely covalent. And so it's so like knowing that ionic bonding is like very, very strong and preferable. Covalent bonding is not as preferable. So it's something that's almost purely covalent, lacks the symmetry. It's not a very strong bond, right? So you don't see a lot of organohaldies. They mainly react with water and they're just hydrolyze. So they are air sensitive because there is moisture in water. Moisture in water. There's moisture in air. But next, brominated stuff. So acorn worms. So apparently there's another. I was watching a YouTuber who made literally a video this week about acorn worms, and I was like, no, I don't want to talk about them. But like, anyways, yeah. I'm a little bit exhausted, not gonna lie, because this is already my 4th attempt trying to record this video. But basically, acorn worms are very interesting because they produce brominated stuff, right? I used some very old papers because the textbook I was inspired by was quite old, and I wasn't really that fascinated by acorn worms. Like, I think there's much more interesting stuff that I'll get onto later in the video. But basically, acorn worms can use these brominated stuff, and they're basically very basic when they're, because acorn worms are digging in the dirt, right? They are mostly in the ground, so they're not very much exposed to oxygen. But when they do go into air, it kills the bacteria, which was interesting. That's what the paper, this one said. And they observed that anaerobically the bacteria were actually rapidly consuming these 2,4-dibromo. They're probably also consuming 2,6, but the paper for 2,6 was just identifying 2,6. And so acorn worms are actually producing a lot of other brominated stuff. And they're quite interesting to me because it's quite clearly meant for one electron shuffling, and it's like not very typical conventional symmetry for electron shuffling. Normally when you're doing electron shuttling, normally you're doing it with a metal center because metal centers are very useful for transferring electrons. So it's kind of, you will be losing some electrons as this goes on. So I think that's quite interesting that, you know. But anyways, I'm going way off track. But basically, I put these structures here, these ones on top, just to tell you how to read skeleton structures. Take this carbon, for example. Like each joint is a carbon, right? So here, this bending point is a carbon, and this one's also. And so okay, this carbon has a double bond to this carbon that has another single bond to this carbon. Where's the fourth bond? Carbon makes 4 bonds. So in organic chemistry, since we're dealing with so much carbon and hydrogens, we only show carbons as joints, and we don't draw the hydrogens. So there's actually a fourth hydrogen, we just don't draw it. We only draw hydrogens when we're dealing with reactions with those hydrogens. So if like there's something that's taking off that hydrogen or something like that. What else? Oh yeah, we also don't show lone pairs because bromines should have like 3 sets of lone pairs. But anyways, and I tell you this to tell you about polychlorinated aromatics. So these are pollutants and they're carcinogenic. Yay! They mess up with the hormones in our bodies, basically. And so here it's showing that chlorines are bonded to nothing, right? But that's not really what it's trying to depict. It's trying to say that you could have n, where n is any integer, of chlorines on this ring. And clearly it has to be like a max of 4. Same here, max of 4, because there's 4 carbons, so, you know. Also stands for an integer. And so you can have any number of chlorines here. And so when there isn't a chlorine, right, there's going to be a hydrogen. So these 4 could be all chlorinated. This one could be a hydrogen. This one could be chlorine, and then hydrogen. Maybe the longitude positions versus latitude positions are chlorine versus hydrogen, who knows? Just for example, right? And so these things are also naturally occurring, and they come from very high heat processes. So like forest fires, whether they're artificially induced or, you know, naturally occurring, because, you know, Native Americans were inducing forest fires, so they have a little bit more control of them. They also come from mining, and they also come from volcanoes, right? And, like, you know, atmospheric transport. And so but like, it also comes from other side products from organic reactions. So, for example, it's a side product of Agent Orange, which was used in the Vietnam War. Agent Orange is not displayed on the screen. It's not these two things. Agent Orange is used as basically to remove leaves from trees. And so, you know, obviously the Vietnam War, guerrilla tactics, you know. But basically, these compounds are very synonymous with humans, right? Like, there's a whole lot of myths about humans gaining fire and how fire was important for, like, surviving the night, society for cooking food, all this stuff. And so there's a whole lot of myths and, like, societies that are just, should I say, based on fire, that have, like, rely on the symbol of fire a lot, you know? It's like the symbol of passion, surviving, like destruction, wrath, right? And so these compounds have always existed before us, right? They were produced by volcanoes. And yet there are bacteria that could, you know, digest this stuff. You know, it's Dehilococoides. Probably butchering it. I never actually had to say it out loud. Mainly because in lab we just refer to it as that bacteria or this bacteria or whatever, and like whatever set we're studying them in. But anyways, where was I? TCDF, bacteria can consume them. And so like bacteria have learned to basically digest this stuff and like gain energy from breaking these carbon-chlorine bonds before humans even started using them dramatically, you know, like even like small occurrences, like, you know, like when you go to a campfire, you know, and you like roast your marshmallows and you put out a fire, right? There is going to be this stuff in the campfire. It's just going to be so tiny you might not be even able to measure it, right? Who knows? Maybe it's a lot, who knows? So, but like this has been going on for a while, like even in like the Dark Ages or Middle Ages when they were having like these small fires, this was there, you know what I mean? And so like this is kind of like our fingerprint, right? On the human, like humans' effect on the planet is very much present by these dioxins. And so, yet bacteria have evolved to eat in these things, which I hope gives you hope more than anything else, that, you know, these pollutants, these things that are symbols of humanity, is the worst traits of humanity, war and fire, you know what I mean? That they have been successfully removed by bacteria, you know, and it's like, you know, you could either see it as pollutants, like, oh my god, they're going to cause cancer, oh my god, it's the death of all humanity, or you can see it as, like, you know, they've always been there, and they always will be there, and bacteria will always have food, you know what I mean, like, but, you know, it's, again, this video is more to offer hope and a different perspective on pollution more than anything else. So the next thing I want to talk about is white rot fungi. What's very neat about white rot fungi is that they can basically take chlorine ions, put it on, you know, an aromatic ring, and then use this to make hydrogen peroxide, which can then be used to degrade lignin and other chlorinated pollutants, which is, to me, like, super fascinating. I don't know, I find it, like, really, really cool. You know, like, defeat the evil by becoming the evil type of thing. Anyways, I also have a Black Dragon sealed in my hand, but anyways, I think it's just really, just kind of cool, that, this really occurs, you know? But here's, like, a more detailed and accurate depiction of it, and again, this is coming from the textbook, but the textbook doesn't show, the chlorinated aromatic stuff being used, you know, this thing, it doesn't show it, like, they produce various compounds similar to this, right, to make the hydrogen peroxide, which then eventually can be used to take this pollutant and get energy from degrading it. Like, this one is responsible for destruction of the ozone layer, you know? For example, what else? Oh yeah, so another interesting thing about white rot fungi is that depending on what halogen you give them, you can have different things used to make hydrogen peroxide. So when you feed them with chlorines, right, they produce these series of compounds that can be used to make hydrogen peroxide, right? When you give them bromine ions, would you look at that? It's the same thing, but instead of a chlorine, it's a bromine. And here also, chlorine, chlorine, bromine, and bromine, just swap. Here's the same compound, but instead they have chlorine here. And that's because it's just so much more energetically favorable to use chlorine than bromine, and like the fact that chlorine is so ubiquitous in the environment, it's like everywhere, that it's impossible to fully remove, that the fungi in the test got a hold of it and used it instead of the bromines. But like here, like they were also able to detect this, right? There are like numerous compounds that they did not detect, obviously, because, you know, where's this bromine analog? Where's this chlorinated analog? You know, they're not there. So obviously there was a lot more that they simply just did not detect. And then when they fed them with iodine ions, they actually did, well, they found this, and they assumed that it was actually a hydrolyzed, because don't forget, iodine bond is very weak in success, and it's like very easily replaced with water. So they very much suspect that, you know, this actually was iodine, just immediately did not, in the presence of water, just decomposed and like did another reaction. I really kind of wish they commented on how far this iodo compound got into the process. Like, did it immediately hydrolyze as soon as it got out of the production site, or did it like get hydrolyzed as soon as it met the hydrogen peroxide after making it? I don't know. I wish they kind of commented on that. But what do you think happened when they fed them with fluorine ions? Nothing, right? Because, as I mentioned in the unique geometry of PFOA, it takes too much energy to actually use fluorine ions, right? So it's not so the fungi didn't use it. In the paper, there's just one line about it, and you know, they don't talk about it at all if it just flat out killed the fungi or not. But anyways, just a little bit of a pet peeve. But I really did like this paper. It was a lot of fun. Especially since I use chemistry skills, and like, you know, I am a chemistry major currently in environmental science lab, and I really want to find my place in environmental science. I want to continue it, but like, you know, why would environmental engineers hire a chemist when they could hire an environmental engineer, right? So like, you know, this paper gave me some hope, like thinking like all the environmental engineers don't know what an HNMR proton or stuff is, and it's like, yeah, I could read this so easily, and they probably have no idea what a GC is. Like, I mean, okay, they know what a GC is, like, but you get what I'm saying, right? Like, I was purposely trained to use these devices. Meanwhile, not every engineer is, you know? But anyways, what's really interesting is that they were actually able to detect di- and trihalogenated methanes. Example given, chloroiodomethanes. Which is really, really interesting. Because these halogenated methanes are actually responsible for the ozone hole. Yeah, when you get a halogen, bromine and chlorine specifically, and especially bromine, they're really good radical quenchers. Chlorine is a lot more reactive than bromine, but bromine is like the perfect quencher. And so when they get into the ozone layer, the ozone cycle, right? The ozone cycle is just a series of reactions, of just radical reactions, right? So as you can imagine, bromine, the radical quencher it is, just quenches all of it. And so it's really a question if the halogen can get up there, because usually they're very heavy, and so like, you know, heavy things don't float, basically. I mean, asterisk on that, but like, because, you know, anyways, you get what I'm trying to say. So methanes are just light enough to actually get those halogens up there. And so the fact that even pollution has a role, like even these like pollutants are detected, because in this paper they were not feeding them like, you know, these di- or trihalogenated methanes. No, they were not feeding them this, you know, they were not. This is proposed by the textbook, what has been observed, you know. In this paper specifically, they were not feeding them this. They were specifically feeding them chlorine, bromine, and iodine ions, and they were determining mechanistic details of other things that I just did not talk about. So they did not put the stuff in, and they somehow measured it, which is just fascinating. And again, these things are responsible for ozone hole, right? Basically, like for depleting ozone. And it's like, I assume you very much know that the ozone hole exists and that the Earth is not flat, etc., etc. So I'm not going to try to prove it to you, but It's really just gives a new perspective that white rot fungi were producing these things before humans were producing them for themselves. You know what I mean? And it's like, even these things had a place and role to play in the environment before humans started artificially introducing these trihalogenated methanes, or like tetra. For example, like this is a refrigerant, right? This is human-made. So it's like very interesting to think about that, even pollution has its place, which goes against the very simple school of thought. I shouldn't say it's simple. A school of thought that pollution is just displaced matter, like by simplest definition, But anyways, there are actually other naturally occurring organohalide halogenated methanes, and they're produced from volcanoes. Specifically, this is a list of halogenated compounds from volcanoes, and as you can see, there's fluorotrichloromethane, chloromethane, bromomethane, iodomethane. I just based a whole list of them, right? And so it's like volcanoes, they easily emit stuff into the ozone cycle, right? Because it's a gas, it floats, blah blah blah. And so, all these stuff, volcanoes are like responsible for like land formation, basically, right? Like, I actually don't know that for a fact. Don't quote me on that, but like, I never took like geology classes, so like I have no idea. But like, they very much are responsible for the creation of like new land and stuff, and like, they have existed before us. You know what I mean? Like, before humans, and the fact that these things existed back then, it really, I hope it provides you a new perspective that there is a role in time and place for everything, including pollution. And like, look, this is just the stuff that we could measure, right? Like, bacteria could have evolved from times of volcanoes to have eaten and like grow on this stuff. This is just the stuff we're measuring, because if you recall, I actually did mention that there are other pollutants, specifically these two ones, that can be produced by volcanoes, but they did not detect them. And that's kind of a thing about environmental science. It's not as analytical as physics. Basically, every sample is a variable, and it's really a question of what you want to measure and how you can measure it. Because each sample has so many variables, it's so variant, it's so different. Like, 1 inch of dirt is not the same as the next one, quite literally right over. And it's like, there are so many variables and so many things to find and test and like, to analyze, that's just simply not possible. And so you really need to be selective of what you're finding and what you're measuring, right? And so in this analysis of volcano gas, they did not find these polychlorinated aromatic systems, right? So isn't that kind of interesting that there's for sure way more halogenated stuff that we did not measure and that we just don't know exist yet? Because, like, remember, 75 years ago we thought there was no such thing as a naturally occurring organohalide, but now, like, there's like known 20,000 of them, you know what I mean? And there's even like fluorinated stuff, you know what I mean? Like, surely there is some biodegradation of fluorinated stuff. So let's talk about trifluoroacetic acid. Trifluoroacetic acid is becoming a larger and larger issue, mainly because concentrations are on the rise. As you can see, as time increases, as years go on, trifluoroacetic in picograms per kilogram of dry weight of leaves, and as you can see, the concentrations are just increasing and increasing. And so there is no blatant explanation why there should be so much trifluoroacetic acid in the environment and why it's increasing so much. Like, there are probably multiple different sources that we just don't know. I have been looking into trifluoroacetic acid recently. So yes, hydrofluorocarbons, I think it's specifically 134A, that can be used to make trifluoroacetic acid from the ozone cycle. Medicine, I have not read a paper about that. Agricultural, yes. Natural sources is a debate between civil engineers and chemists. Because there is some naturally occurring carbon tetrachloride, right? But it's usually trapped underground. And so it's like, there are some people who say, yeah, it can easily turn to trifluoroacetic acid. And, you know, the chemists are screaming, but where's the oxygen coming from? Because trifluoroacetic acid is 2 carbons. One carbon has 3 bonds to fluorine, and the 4th bond is to the other carbon, which is a double bond to oxygen, and then bonded to another oxygen with a proton, or hydrogen, right? And so there's quite a lot of evidence that it's just atmospheric deposition of trifluoroacetic acid. And so that's why leaves are so interesting, because like you could have evergreen trees, right, that last through winter, they keep their leaves, and they'll be collecting the trifluoroacetic acid from the atmosphere and deposited it onto their leaves. Meanwhile, in like the summer, it'd be going onto both of them, and basically you have like this really cool cycle of measuring trifluoroacetic acid throughout the seasons and throughout the years. So that's kind of cool, right? The really fortunate thing about trifluoroacetic acid is that it really, really loves water. And that's why it could actually easily partition onto the pine trees, because pine trees, I think, unlike on these evergreen trees, are like actually mostly fat, if I recall correctly, and that the other leaves that you see fall off and dry on the winter are mostly water. At least from my own understanding. Again, I don't know anything about ecology, you know. I'm a chemist and I'm today. And so you can naturally get you can measure trifluoroacetic acid on leaves, right? You could also measure a million other things that are on leaves, right? Because there are other pollutants that are in the sky that go into the ozone cycle, go through it, and transform. And leaves are the filters of the sky, while ozone is the vacuum cleaner, right? And so it just drops onto leaves, and you could be measuring a million other things, right? This paper is specifically measuring trifluoroacetic acid. Oh yeah. This is also, again, another thing about environmental science. We don't really one thing is that we really deal with massive error bars, because we simply just don't know. There's way too many variables, and there's just no real practical way of making sure we're certain. We use a whole lot of statistics, don't get us wrong, but like, you know, like, where are the error bars? Was this increase as significant as it really seems? Because like in this paper, they do not talk about the sudden and rapid increase in 2009, you know what I mean? And so like, how much of it is due to the error bars and how much of it is not? Like, why don't they report the error bars, you know? In like environmental science, you know, we very much have to rely on error bars, because like, in comparison to chemistry, I have never seen a paper in analytical chemistry use an error bar. I'm sorry, I haven't. But that's because I don't really mainly read analytical papers, so like, you know, I'd have minimal exposure to it. I'm sure there are some, but like, I have never seen an error bar on a chemistry paper. Meanwhile, environmental science papers, I've seen error bars constantly, you know, and they're quite massive. But yeah, basically, we have no idea where all this massive concentrations and amounts of just trifluoroacetic acid is coming from. We just simply don't know. And so let's talk about biodegradation of trifluoroacetic acid. There has been only one report of biodegradation of trifluoroacetic acid. It's from 1994. And it has not been reproduced since. You know, back then, like, you know, the internet did not exist, you know, so it's like, communications were not as spontaneous as ours, and I think that, you know, it would have been a much more interesting case if it was modern day, you know, foreshadowing. But here they this is a letter. Basically, a letter is the snowball that turns into the glacier, right? It's a very exciting report in science, and you have to scream about it, right? So you found something amazing, you have to scream about it. So you put it in a letter and not a paper, because a paper is something that is fully fleshed out. It is fully peer-reviewed. It is thoroughly checked over and critiqued, and to get the best possible product. But a letter is much more about exciting things, new hard-to-line things, right? And so in this paper, they were reporting the degradation of trifluoroacetic acid. And this paper has not been reproduced since. Yeah, in the 30 years, no one has been able to reproduce this paper. And when I talk to older scientists about this paper who were actually there for would I say the craze? I guess the craze of this paper, it's very much a nostalgia, 30 years ago. Wow, no one has been able to reproduce it. And it's not like the intense emotions I get in comparison to Peter Jaffe's paper. So, trifluoroacetic acid is a type of PFAS. It really comes down to the semantics of it, which I really should make a video about. But anyways, the first report of a legacy PFAS, which is PFOA and PFAS, the first reported biodegradation of it is by researchers in Princeton, specifically Peter Jaffe, right? And Shan Huang, I butchered it, sorry. And so they report it, right, as an article, which is really interesting because maybe I'll talk about this later, but anyways, that's interesting. They report it as an article, and it's from 2019. And so as you can see, there has been 2 additions / corrections. However, these are really rebuttals and a defense of the rebuttal, basically, right? And so I had to actually get these pictures from the second response, because these pictures were not provided in the original paper. If I'm just going to be so arrogant and complain about this paper, when I really, really want to understand and grasp a paper in its full glory, right, I am reading the paper alongside its supplementary information, because most papers come with supplementary information, and that's where usually all the real fun stuff is, in the supplementary information. Papers are good, but if I really want to know it, I'm just reading them at the same time, 2 fingers on the place, And so in this supplementary information, it is just the graphs that are originally in the paper, which is a choice. It's like I said before, supplementary information is supposed to be the real meat and potatoes of it all. Meanwhile, this paper just did not. In fact, when our lab tried reproducing this experiment, we also found it very, very vague, which is part of the first attack, right? But keep in mind, this paper was published in 2019. The first critique was in 2023. 4 years later. For 4 years, no one was able to reproduce it. And so obviously they critique the science and the actual technique, but again, this is super niche of niche, we're dealing with PFAS, and then we're dealing with this very specific paper, and then we're dealing with critique of it. No time for that. It's already 40 minutes? Yeah. No time for the nuance of it. However, one quote that really sums it up is, "We find the methodology provided by the authors to be opaque and problematic. The PFAS analytical methods described in this paper have errors, inaccuracies, and omissions, precluding other researchers from validating the quality of the chemical analysis or replicating the work. Similarly, the molecular microbiology methods presented lack the necessary detail and appropriate quality assurance and quality control." Okay, a whole lot, but basically, they're saying it's very vague. I'm yeah, we also thought it was very vague when we tried reproducing it. There are other scientists that had questions, and they directly reached out to Peter Jaffe. There's people like us who just didn't bother, and it's like, okay, fine, we'll just try to replicate it to the best of our ability. Spoiler alerts, we're getting no results. And then there's these scientists who, again, are coming from all over the world, right? We have someone from McGill University, Toronto, Australia, Colorado, again, Australia, California, Indiana, right? Like, these scientists are communicating to each other and asking, why isn't this working? And so they, have to say, okay, we have to do actual science here. No one's been able to reproduce it. And so they obviously have to critique the paper and explain what they thought was wrong. And they do. Again, we just don't have time. And this is just a summary quote. But let me talk to you about the names on this paper, on this critique. Xinxia Lui, butcher that, sorry. She actually found biodegradation of a certain type of PFAS in 2010. Yeah. And her work has actually been replicated. In fact, I was just reading a paper the other day, I think it was like from 2023 or 2024, where they were studying this biodegradation. And so they took this specific PFAS and they got biodegradation of it, and they were specifically looking if this one of the biodegradation products is trifluoroacetic acid, which it was, which was just like, but this paper in 2010 did not report, the original report did not report any trifluoroacetic acid because they were not measuring for it, but this paper that managed to replicate it in 2023 did manage to replicate it by themselves, and they were able to quantify some trifluoroacetic acid, which is just absolutely spectacular, right? Another source of trifluoroacetic acid and why there's so much of it. And so let's just talk about, but this is the original author who found one of the biodegradations of one of the multiple different types of PFAS. Elizabeth Edwards is also a big name in this field. She and her team of senior engineers are all very well experienced, very intelligent people, and they were not able to reproduce it. And like I said, she and her team of senior engineers, yeah, they were not able to reproduce it, and they felt they had good reason to critique this paper. The next big name I kind of want to talk about is I'm a little bit of a fanboy, Christopher P. Higgins. I dream of joining his lab one day as a grad student, and it's highly unlikely. But he's from the Colorado School of Mines, and I also really like his research. I think he's like a really respectable name and like really, really cool scientist. I should probably be looking into these other guys like on the paper too, because they're clearly also probably big shots, because like, let's be honest, you're not going to see like Greg on this list. It's not going to say and Greg, you know what I mean? Like, they're all probably like really big shots who know each other and like, in correspondence and know, like, other bigwigs, so I should probably look into them, but I don't recognize them. But as we saw before, Peter Jaffe had a response to this critique. And again, he goes through the nuances and blah, 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 but the real exciting part is that, quote, "We made the strain available to several researchers and graduate students at other institutions. Unfortunately, in many cases, the strain did not grow, and even the ammonia oxidation was barely detected," which is basically a sign of life for this specific bacteria. "We have worked with many of the recipients of the strain to ascertain that they were familiar with the techniques and are puzzled about the low success rate in keeping the strain alive." Obviously, as I said before, they critique the messes, and they do provide a little bit more information this time. This time, they actually provide pictures of how they're growing the bacteria, basically, right? Which is like, okay, whenever I'm reading papers that are trying to grow bacteria under these very specific and controlled environments called microcosms, basically, they almost always provide pictures. So the fact that only now, after a critique, they provide pictures is kind of like baffling, because, it should be in the original paper. Almost all papers I read about microcosms have it, something about, their microcosms, you know? Like, either it's in the supplementary information or it's in the actual paper itself. So the fact that you gotta get to critique it and then you get it in the response, it's like... And he does provide a little bit more methodology on, in his work, that he didn't provide in the original paper. And like I said, yeah, we did try to reproduce it, and yeah, it was pretty opaque as proper criticism is, and and it's like, I think it's really interesting. One, like, we have this like direct comparison between like when we lacked like such direct means of communication, like quite literally people across the world are communicating with each other, versus trifluoroacetic acid when like we just did not have that. I think it's also really interesting that we have like very tiny glimpse into this massive world of potential biodegradation of PFAS that we just simply are not aware of. Like, first trifluoroacetic acid and now this? Like, come on. It's like... It's just so interesting that really there might be a world where, trifluoroacetic acid does have some natural source, maybe very tiny, and we were just not aware of it, and maybe, like, the bacteria have been eating this for, like, eons, and we're just not aware of it, you know what I mean? And it's, like, it's so baffling to think that, we just haven't measured it yet. We're just not aware of it yet. And it's just, like, I don't know, it's also, like, so encouraging. It's, like, provides a sense of hope. It's that we have the answer somewhere on this planet. We just haven't found it. Because don't forget, bacteria are small, and they are ubiquitous, and they are just everywhere in the world. And the world is absolutely massive. It's like, surely if you believe that the space is big argument and that aliens exist, you must also believe that surely there is some microbial biodegradation of PFAS. We just have not found it yet. But anyways, that's it for this video. We're excited. Links in the description, yada yada, slide number. And thank you for listening. Have a good day.